In the last video, we discussed about the atomic mass unit and learned how it is related to gram. Atomic mass unit is a unit of mass at the atomic scale. One atomic mass unit, or AMU, is equal to mass of a carbon-12 atom divided by 12. This is represented as U or AMU, as we represent bigger mass in grams. There we saw mass of one carbon-12 atom is 1.99 into 10 to the power minus 23 grams. However, the number was not known before. This is the result of recent measurements with the help of advanced mass spectrometry instruments. Then, one natural question may arise: how did the early chemists estimate the mass of atoms? Historically, chemists could not measure the actual mass of individual atoms. They could only compare the masses of different atoms. For example, they found that an oxygen atom is about 16 times heavier than a hydrogen atom. This led to the concept of relative atomic mass. Then, how did they estimate the relative mass? Let's try to visualize this. By the time chemists had established that the molecular formula of many compounds, like for water, it is H2O, they also knew from experiments that 1 gram of hydrogen combines with 8 grams of oxygen to form 9 grams of water. This is a macroscopic measurement. There is no need to be worried for the atomic scale, since each water molecule contains 2 hydrogen atoms and 1 oxygen atom. Let's say our 1 gram of hydrogen contains X number of hydrogen atoms. As each water molecule requires 2 hydrogen atoms for every oxygen atom, the number of oxygen atoms needed must be exactly the half of the number of hydrogen atoms. Therefore, 8 grams of oxygen must contain X by 2 number of oxygen atoms. Now, we can do simple mathematics. If 1 gram of hydrogen contains X number of atoms, then the mass of one hydrogen atom is 1 by X grams. Similarly, if 8 grams of oxygen contain X by 2 number of atoms, then the mass of one oxygen atom will be 16 by X grams. So the ratio of mass of one hydrogen atom to the one oxygen atom is 1:16. From here, we can say that one oxygen atom is 16 times heavier than one hydrogen atom. Now, if we choose the atomic mass of hydrogen as 1, then the corresponding atomic mass of oxygen becomes 16. This is the relative atomic mass of oxygen is 16, taking hydrogen as the reference with an atomic mass of 1. While doing so, we should not be worried about the unit, as it is a relative term, so the units will get cancelled. This is the beauty of relative atomic mass. So by doing reactions and quantifying the product, it is possible to determine the relative atomic mass of the elements. We can calculate relative atomic mass of all other elements, taking hydrogen atomic mass as reference. This is how the early chemists used to calculate the relative atomic mass of all elements. It is important to note that, initially, chemists simply assigned the atomic mass of hydrogen to be 1 because it was the lightest known element and served as a convenient reference. Today, we use carbon-12 as the reference material and calculate the relative atomic mass of other atom based on how heavy they are with respect to carbon atom. The relative atomic mass is defined as the weighted average mass of the atoms of an element relative to 1 by 12th of the mass of a carbon-12 atom. The number that you see in the periodic table, such as for hydrogen, 1.008, for oxygen, 15.999, all are the weighted average relative atomic mass of the elements with respect to carbon-12. Now, you are introduced with a new term of mass, which is average mass of the atoms. Let's see what it is. Earlier we saw that an atom's identity is defined by its atomic number, which is the number of protons present in the nucleus. For example, carbon has 6 protons, which gives its identity. But naturally carbon occurs as a mixture of 3 isotopes, such as carbon-12, carbon-13 and carbon-14. All have same number of protons, but different number of neutrons, hence possess different atomic mass. All isotopes have different masses and different natural abundances. For example, carbon-12 has a relative abundance of 98.93%, carbon-13 has a relative abundance of 1.07%, and carbon-14 has a very little presence, which is in parts per trillion. Each isotope has different mass, and all are evaluated using the same carbon-12 atom as the reference. As we know, the pure atomic mass of carbon-12 is exactly 12.00 U. On that scale, the pure atomic mass of carbon-13 and carbon-14 are 13.003355 U and 14.00324 U, respectively. But in nature, the carbon that we find is always a mixture of carbon-12, carbon-13 and carbon-14 atoms with the same abundance. Therefore, the mass of carbon atom represents the weighted average mass of the 3 isotopes. That makes the average atomic mass to be equal to 12.011 U. The atomic mass that is written in the periodic table is this. So it is more appropriate to say, the average atomic mass of an element is the average mass of all its naturally occurring atoms, weighted according to the relative abundance of each isotope.